Alright, now let's talk about comparison between classical and modern theory. I love this part, okay, because after my explanation here, you definitely can see what's the difference between the classical physics and quantum physics. Okay, well, what I can say is, first of all, classical physics failed to justify the photoelectric effect experiment. It's not you have learned this classical physics in semester 1. Okay, you have learned this in semester 1. Now you learn about quantum physics in semester 2. Okay, sem 1 classical physics, it happens for certain conditions, but talking about photoelectric effect, it didn't happen that way. What I can say is it didn't happen that way. But when we're discussing about photoelectric effect, what really happened is under quantum physics. So photoelectric effect has justified the happening in quantum physics. Okay, so now let's look one by one. Okay, we can say the quantum physics is the actual happening in photoelectric effect. In photoelectric effect, the effect that you see just now about the particles of light, yeah, all these can eject or cannot eject the electrons, yeah. When we have talked about these, E equal to Kmax plus work function, HF more than the work function, the frequency must more than the threshold frequency, the wavelength must be less than the threshold wavelength. This is the quantum physics. Okay, this is the quantum physics. This is not classical physics. Classical physics have their own understanding, but that does not happen in this case, in this photoelectric effect. Okay, so let's look at, first of all, look at classical physics. You have learned this in semester 1. Try to remember it. You see, what he says, the first argument for classical physics, the comparison between classical and quantum physics is the feature of threshold frequency. For classical physics, they believe that an incident light of any frequency means what? Any frequency is the different type of light. Okay, okay. First of all, we look at this one. We look at this one. Maximum kinetic energy of photoelectron, it depends on light intensity. Whereas the quantum physics says depends on light frequency. Okay, first of all, if you look at my previous video, I did explain about intensity and frequency. What is light intensity? Again, I just want to emphasize here, intensity is the brightness of light. Brightness of light. Frequency, or we can say, depends on light wavelength. Different frequency or different wavelength means different type of light. Different type of light. Okay, when we talk about brightness, it can be the same type of light. Okay, it can be still the same type of light. Okay, same type of light. This one doesn't this one doesn't depend on intensity at all. Okay, when we talk about intensity, it can still be the same type of light but with different brightness. So let me redraw it over here. Okay, like this one, let's talk about red light. We have a dim red light, we have a very bright red light. Very bright red light, this one. Still red light, same type but different brightness. Yeah, so this is the dim red, this is the bright red. Understand? Bright red. Whereas different frequency or different wavelength means different type of light. So we can have red light, we can have violet light, blue light. Yeah, let me use the blue light. This is the blue light. Okay, so this is called different frequency of light. We have a red light, we have a blue light. Okay, This is different frequency. So last time we did learn if red light has very high, low frequency, long wavelength. But blue light has a very high frequency and short wavelength. Alright, that's it. Okay. If you still remember, red light is 400 nanometer, blue light is around 600 to 700 nanometer wavelength. Okay, wavelength. Okay. Classical physics. Yeah, let's look back to the first one. Classical physics. He says that talking about threshold frequency, he says that an incident light of any frequency. So now do you understand what is meant by frequency? Frequency means the type of light. Is the type. This one means the type of light. Type. So what he's saying is that any type of light can eject electron. Can eject. That means no matter what light, no matter what frequency, it does not have a threshold frequency. That means red light can eject, blue light also can eject, any light of light, radio wave can eject, X-ray also can eject, any ray can eject electron. Any ray can eject electron. Does not has a threshold frequency, independent of frequency, as long as the beam has sufficient intensity. So what he means is, what he more concerned about is the intensity. What he more concerned about is the intensity. Must have sufficient intensity. That means all light can eject. All light can eject, but the higher intensity of light can eject faster. You see, this one also got slow ejection and fast dejection because later on we talk about delays. Delays here. So what he's trying to say in classical physics is, red light can eject. Maybe the brighter one, the bright red light, can eject even faster than the dim red light. Yeah, this one we can say dim red light. For classical physics, he says that the bright red light has higher intensity. And then it has more energy. Because talking about intensity, in Sem 1, you did learn about intensity. What is intensity again? Maybe we look at the energy of light first. Energy of light in classical physics. For energy of light, it depends on the light intensity. Whereas the modern physics, the energy of light depends on light frequency. So intensity is about the brightness. Maybe he's saying that the dim one, the dim red light, the dim red light, less energy. Still talking about the same type of light, red light. Dim one is less energy, the bright one more energy. The bright light has more energy, the dim light has less energy. Because for classical physics, he's saying about the intensity. Because what in classical physics he mentioned, what is the equation for intensity? Still remember the equation for intensity? Let me show you. The intensity for classical physics, intensity formula is power over area. So he's saying that power is actually energy. Power is energy over time, isn't it? Energy over time divided by area, and then area. So energy for wave, energy for the wave, the total energy for wave. Still remember the total energy for wave? The total energy is, we learn, is half m omega square amplitude square. Okay? So you see that? For intensity in classical physics, he relate the intensity to the energy of light. Energy of light. But in quantum physics, the energy of light is not this formula. This is for classical physics. Okay, this is for classical physics, which doesn't happen in photoelectric effect. Okay, so the energy, maybe I should write here. Maybe I write here energy over time. Yeah, which is the power. Power is energy over time. So in classical physics, he's saying that the intensity, he relate intensity is proportional to the energy. So what he's saying is that the higher the intensity of light, the more the energy of light. The more the energy of light. But that is for classical physics. But modern physics, he does not relate energy to the intensity. He relate energy to the frequency, which another formula used is this one. He's talking about photon. He's talking about photon. He's talking about particles of light. Particles of light. Particles of light. That means he view the light in terms of particle. It has many particles. Okay, particles of light. All of these are called photon. And each photon has energy hf. So he's saying he relate the energy of photon or energy of light to the frequency. This is just for one photon. This is just for one photon. This is just for one photon. But for if the whole light, let's say the number, this is you have n particles. You have n particles, n photons. Okay. Here you have n photons. So the total energy of light is the energy of light would be n times hf. Yeah. The energy for one particle multiplied by the number of photons. Okay. This is energy for light. So for energy for light depend on frequency of light. And what is frequency? Frequency is different type of light. So energy of light in quantum physics depend on the type light frequency. So what I can say is the higher the frequency, here you see, the higher the frequency of light, the more the energy of light. That means like red light has a low frequency, isn't it? Red light has a low frequency. So he's saying here the red light has low frequency, so it has maybe this one I just put in symbols, easier to understand. Okay, this one is the energy, dim one less energy, bright one has more energy. For red light, yeah, for quantum physics, he's saying depend on frequency. That means the red light has low frequency because of low energy. Has a low energy because it has low frequency. Yeah, red light has low frequency, so has low energy. But for the blue light, maybe I should use this one as a red color. Yeah, red, just put red. The blue one has so the blue one has more energy. And the blue one has more energy because it has higher frequency. So can you see that the difference between classical physics and modern physics? Classical physics, same type of light, red light. If dim, low energy. If bright, more energy. But for quantum physics, different type of light. Red light and blue light. Red light, low energy. Blue light, high energy. So, if talking about eject or cannot eject electron, he say that he depend on intensity, must use bright light. Bright light can eject the electron faster. Dim light take a longer time to eject electron, because talking about emission of photoelectron, classical physics, he say that any frequency can eject. Any frequency can eject. That means any type of light, no matter it's red light or even radio wave, also can eject. Any light can eject. But maybe the low intensity one, the dim light, ejects slower. The bright light eject faster. Yeah. Maybe you can say some delays. Maybe we can say the dim one. The dim one eject slower, takes some time to eject, but the bright one eject faster. Eject faster. Why we have a slower and faster here? We must understand classical physics, but that does not happen. Why we have eject faster and eject slower? Yeah, this is just their prediction. Why eject faster and why eject slower? For D1 take a longer time to eject. There are some delays. Bright light eject faster. Why? Because they view classical physics, they view the light as a wave. That's it. They view the light as the light is a wave. Wave. But for the modern physics, they view the light as particles. Classical physics, they view the light as a wave. But modern view the light as a particle. You see, classical physics, I view the light as a wave. Wave means that's why we learn about this intensity, isn't it? Power over area, the energy of light, the total energy of light. We learn this in classical physics, half m omega square a square. So remember the energy, this energy, the total energy of light is we use half m omega square a square. Where do you learn this this equation? You learned that in mechanical wave. You learn this in simple harmonic motion. You learn in the simple harmonic motion. You learn also in the mechanical wave. So that's why classical physics, we view the light as a wave. Simple harmonic motion also about wave, isn't it? So classical physics, he's thinking the light as a wave. As a wave. Yeah, he's thinking the light as a wave. So any light can eject the electron, any frequency, any type of light. The dim one eject slower, the bright one eject faster. Why he say bright one eject faster? Because the bright one carry more energy. The bright one carry more energy. The dim one carry less energy. Dim carry less energy. The dim red light carry less energy. The bright red light carry more energy. So there should be some delays to emit electrons from metal surface. So maybe I can say is so classical physics, he view the light as a wave. So it's like where should I draw? I just draw besides here. I just draw beside here. Okay, this is the metal surface. Yeah, please look. This is the metal surface. This is the electron. So in classical physics, he view the light as a wave. Now red light is coming. I view the light as a wave. So this electron, it has some work function, okay, to overcome. So this electron will absorb because the light, it comes energy, the energy is continuous energy. So in classical physics, he view the light as a continuous energy, not discrete. Continuous energy. Continuous energy. But for modern physics, for modern or the quantum physics, they view the light as this is which is proven in the photoelectric effect. Has some work function. They view the light in the form of they view the light in the form of particles. They view the light in the form of particles. Particles carry energy HF. They carry energy HF. Photons. Talking about photon. So which is discrete. The energy is discrete energy. Discrete energy means they are not continuous. They are multiples of HF. Multiples of HF. 1 HF, 2 HF, 3 HF. Maybe we can say if one is the 10 joule, if let's say one particle is 10 joule, so added up all here is 30 joule. You have 10 joule, 20 joule, 30 joule. Added all is 30 joule of energy here. You won't find 12 joule, 15 joule. You won't find value in between. You won't find value in between. Very discrete energy. This continuous energy, that means continuous. That means it absorb. This electron absorb the energy continuously. It absorb 1 joule, 2 joule, 3 joule, 5 joule, 5 joule. That's it, continuous energy. So that's why for classical physics, it's saying that for emission of photoelectron, there are some delays to emit electrons from the metal. That means this electron will take some time to absorb the energy. Because the energy comes continuously. It does not come in particles. It takes some time. So absorb. It takes some time. The light comes as a wave. The light comes as a wave, not come as a particle. This one comes as a particles. This one, the classical physics, the light comes as a wave. So I can say the electron take some time to absorb energy before the energy is more than the work function. This is what we call the delays. Understand or not? So these are called the delays. So this electron, it takes some, because the wave come continuously, continuous energy. So this electron will take some time to absorb, to store the energy, increasing by amount, increasing slowly, until in the end, this energy will be more than the work function. Then this electron can be ejected. So basically, if you think that the light as a wave, continuous energy, any frequency can eject. It just takes a longer time to store the energy, take a longer time to gather the energy. Maybe, let's say the dim light carry less energy. Dim light carry less energy, so it take a longer time to store the energy before that more than the work function, before more than the binding energy. So that's why the dim red light carry less energy. The electron ejects slower because it take longer time to store the energy. But for the bright red light, it carry more energy. Because we're talking about intensity, we're talking about energy. The higher intensity, the higher energy. So for the bright red light, it carry more energy. So the electron take less time to store the energy before it is more than the work function. So it can eject faster because the energy come continuously and the energy come at a faster rate. It carry more energy. So the electron store energy faster. It store energy faster and take less delay to eject. So in either case, dim red light or bright red light, there are always some delay. There are always some delay to store the energy. It's either eject slower or eject faster, but it still got delays. Understand? Any light can eject. Any light. You see this intensity equation doesn't have frequency inside. You see, no frequency. Only the energy formula only have intensity. Don't have frequency. So any light can eject. He said that red light can eject, blue light can eject, every light can eject. Yeah, it just takes some time to store the energy before can eject. So any light can eject. No threshold frequency. No threshold frequency. That means, if we talk about threshold frequency, because frequency is about type of light. If we have a threshold frequency, means certain light frequency cannot eject. Certain light frequency which is higher than the threshold frequency can eject. That is the quantum physics. But for classical physics, there's no threshold. No threshold means all light can eject. This one, all light can eject because it has no threshold frequency. This one for quantum physics, he say only certain type of light, only certain type of light can eject because it got threshold. Because this one got threshold. Understand or not? Only certain light can eject. This one, all light can eject, no threshold. Okay. So look at the quantum physics. Quantum physics, to eject electron, the light must have a frequency greater than certain minimum value. Threshold frequency. That means, what he means here, this one means only certain light type. Just now the classical physics, all light can eject. This one, only certain light type can eject the electron. That means maybe red light, low frequency cannot eject. Blue light can eject. Not like the classical physics can accept all light. This one, quantum physics, only certain light. Like for example, he say like red light. Maybe red light not enough energy. Yeah, the red light energy is lower than the work function, cannot eject. But for blue light, very high energy because very high frequency. You see that? This one, red light, low frequency, low energy, cannot eject. But blue light, high frequency, high energy. So energy more than the work function, can eject. So you see that not all light can eject. Not all light for quantum physics. Not all light can eject. Certain type of light can eject. Certain type, only certain color. Only certain color can eject. So I should I just don't have the space to write. Yeah. Only certain type. Only certain type of light can eject. Yeah. This one, all light can eject. All light can eject, but this one only certain type light can eject. Yeah, because it got threshold. Because this one got this one no threshold. This one got a threshold frequency. When you have when you have no threshold, means all light can eject. When you got threshold frequency, means certain frequency cannot eject. Certain frequency cannot eject. Certain frequency can eject. Certain type of light cannot eject. Certain type of light can eject. Like for example, just now I talked, red light cannot eject. Blue light can eject. So when you got threshold frequency, only certain type of light can eject. Right? So quantum physics does not accept all. Yeah. So it must have a frequency. Only the light with frequency greater than the threshold frequency can eject. Yeah, only certain type can eject, no matter how intense the light. Okay. So, but for quantum physics, about the intensity, it has other understanding. Intensity is about the number of particles. Maybe I can say about the intensity in quantum physics is talking about the number of photons. This is the intensity. I will talk about intensity later. Okay, not now. Right? So, and then for quantum physics, the maximum kinetic energy depends on the light frequency. Okay, because of the Einstein formula. Okay, E equal to K max plus work function. So he's saying that the kinetic energy of photoelectron depends on the frequency. The kinetic energy depends on the frequency. E is actually HF, depends on frequency lah. Okay, the Kmax of the electron depends on frequency. Okay, the electrons are emitted spontaneously, no delay. This one, no delay. Why no delay? Because the light does not come continuously. Not continuous, it's discrete. That means it come in the particle. Electron absorb, release. Absorb, if the energy of photon more than the work function, it absorbs spontaneously. It does not have to take time like the wave to store continuously. Yeah, it's just coming continuous. Energy come continuous. Take some time to store. Yeah, and then this one no need. The energy come in particles. If the particles has enough energy to overcome the work function, it eject spontaneously, no delay. Absorb and eject. Absorb and eject. Understand? The electron absorb and eject spontaneously, no delay. Okay? Energy of light depend on light frequency. Okay, so that's all for this comparison. I hope you understand. Okay, for classical physics, he regard all light can eject, no matter it's red light or blue light. Any type of light can eject electrons. Only thing is the brighter light carry more energy, the dim light carry less energy. But that does not happen in quantum physics. That's really happen. Not all light can eject. The red light, if the red light has less energy than the work function, the red light cannot eject. But the blue light, if the blue light frequency is higher than the threshold frequency, or it has the energy more than the work function, it can eject the electron. So red light cannot eject electron, blue light can eject electron. So not all type of frequency can eject, only certain type of light can eject. Okay? In classical physics, since the light come in the form of wave, so it got delayed to eject electron. But the quantum physics, the light come in the form of particles, so the absorption is immediate. The absorption of energy is immediate. The ejection also spontaneous. Okay. In short, classical physics depend on light intensity. Okay. In short, classical physics depend on light intensity. The quantum physics depend on light frequency. We can say classical physics depend on light brightness. The quantum physics depend on light type. Classical physics depend on brightness. The quantum physics depend on the type of light. Type of light. That's all for this comparison. Thank you.